Let's consider the fundamental theorem of calculus. This is something that we have considered before in a previous video, but perhaps we did not state this explicitly. Right? So let's consider this. This theorem comes in two parts, and the first part we've considered. It says, so let's start with this assumption that f is a continuous function on the closed bounded interval a to b. Right? The first part of the fundamental theorem says that this area function, which is in green on the right, it's this area from some fixed reference point, and in this case we're picking the left endpoint of the interval a, that this area function from a to x is differentiable on the interior, and that the derivative is the function f itself. So area sub a prime of x is equal to f of x. The derivative of that area function is little f itself. Okay, so that's something that we considered. In other words, the derivative of this integral, because this integral is that area function, is equal to f of x. There's a second part to the fundamental theorem. We're going to state it, and then we're going to prove it. In fact, the proof of it is not so bad given the first part of the fundamental theorem. So we're going to use the first part of the fundamental theorem to prove the second part. So the second part of the fundamental theorem says that if capital F is any antiderivative of little f, then the integral from a to b of f of t dt is equal to f of b minus capital F of b minus capital F of a. So if I want to calculate that area under the curve, the signed area, all the way from a to b, so all the way from a on the left to b on the right, then what I have to do, or what I can do, is find any antiderivative of this little f that I like, any antiderivative of this function, plug in b, plug in a, and subtract. It's a very useful theorem. We'll see that perhaps in some future examples. So how do we prove, let's think of a proof of part 2. Alright, so let's think of a proof of part 2. In fact, what we're going to do is we're going to start with that right-hand side, capital F of b. So you need to be thinking that this capital F is any antiderivative of little f. Right? So we're starting with capital F at b minus capital F at a. Right, so capital F is any antiderivative. Well, by the first part, if we consider the first part, the area function, area sub a of x, its derivative is little f. So what that tells us from the get-go is that area function is an antiderivative of little f. And we know that all antiderivatives of this one function, little f, differ by a constant from each other. So we know that, for instance, f, so off to the side here, just sort of as a note, f differs from this area function, area sub a of x, by a constant. So I've just written this in parentheses here. We're going to use that fact. So then capital F of b minus capital F of a, well then that means that this capital F of b, that's the same thing as area sub a of x, of b, plus some constant. And I know that capital F at a would then be area sub a at a plus some constant. And if I carry out the subtraction, I'll see that this one constant is the same exact constant as it is in the second set of parentheses. Then c minus c, I should get area sub a of b minus area sub a of a. This term right here is the area under the curve from a to a. It's the area of a line segment from the curve to the horizontal axis. This area is 0. Right? And so then this is equal to trying to cross my a here. Area sub a of b. Essentially the area under the curve from a to b. In other words, this is equal to, so f of b minus f of a, capital F of b minus capital F of a, is equal to an integral from a to b of f of t dt. That's exactly what we wanted to prove. That's the second part of the fundamental theorem of calculus.